Hey, good morning. Today we are finishing up the first part of Unit 6, the integral. We're looking at Lesson 8, the substitution method again, but this time we're looking at definite integrals. So if you notice my first two examples, I have boundaries on the integral sign. We're talking about A and B here. So with our definite integrals, there's a step that's just a little bit different. Just like yesterday, you want to look for your U, which is not ready yet because my pencil's not ready yet. Hold, please. There we go. U is going to be the x squared plus 1. And du is the derivative of that. It's 2x. 2x dx. So in the last lesson, we were looking at, well, hey, what do we need to do when I'm looking for 2x dx and I don't have it? So I need a 2x dx. Up here, I have the dx and the x, but I'm missing the 2. So what I had said is you can put a 2 in the problem. That's fine. But if you put a 2 inside, what do you have to do outside? You need a 1/2. So this becomes 1/2 the integral of u cubed du. That's good. That's what we did yesterday. Now, here's the thing that's different for today. We have these boundaries. We have this lower boundary and this upper boundary. The thing that you have to remember is these are x values. And my new problem is in terms of u. And so my analogy, it's a little cheesy, but it makes sense to me, is if you're in a foreign language class, if you're in Dr. Wasquier's French class, and you have to translate something completely into French, you can't have English words scattered throughout there. It has to be all French. So all English or all French. So we have to have either all X or all U. You can't have both. So you want to ask yourself, well, how do I take my X and turn it into a U? And if we were in class together, we'd have a long pause and somebody would raise their hand and say, hey, I put it into the U equation. And I'd say, you're right. So what you're going to do is take that lower boundary, which is 0, put 0 in place of the x. 0 squared is 0, plus 1 is 1. And the upper boundary you're going to change. You're going to put 2 in for x. 2 squared is 4. 4 plus 1 is 5. So now you've changed the boundaries and everything is in terms of u. The interesting thing about these is we can finish the problem in u. What do I mean by that? I'll find the antiderivative. The antiderivative of u cubed is u to the 4th over 4. My boundaries are 1 and 5. You don't have to put the x back in. In fact, don't put the x back in. This is where I see a lot of mistakes on these problems. This is still 1/2. 5 to the 4th over 4 minus 1 to the 4th over 4. Fundamental theorem of calculus, part 1. 5 to the 4th is what? 25 times 25. So this is 625 over 4 minus 1/4. So this is 1/2. 624 over 4 minus, no minus because I already did the minus. 624 over 4. Yikes. My mental math this morning. 312 over 4. Because if I divide by 2, 156 over 2, 75 plus 3, 78. I'm going with 78. Now, you can still put this into your calculator into Math 9 and find the answer. That's fine, and we should get 78. But I never went back to x. I finished the whole problem in u. So here's the mistake that I see. Students do a great job. They change the boundaries. We get 1 and 5. That's no problem. And then I see this, and I'm a little hesitant to show you because I don't want to show you what not to do, but they get to this step. And I see 1/2, and they replace the u with x squared plus 1 to the 4th over 4 from 1 to 5. And then I have a 1/2 and a 5 squared plus 1 to the 4th over 4 minus my 1 squared plus 1 to the 4th over 4. What's wrong with this? You're mixing languages on me. You've got these u values out here, which are 1 and 5, but then we put them in place of an x value, which is not correct. You've got both of them going on at the same time. If you choose to put an x back here, these boundaries must go back to an x. So it can't be 1 and 5 anymore. You have to go back to the 0 and the 2. You have to go back to the 0 and the 2. And you could put in the 0 and the 2 and it would work just fine. In fact, you get 2 squared, which is 4, plus 1, which is 5 to the 4th. So you get your 625 over 4 minus your 1/4 with the 1/2. And so you kind of pick up back there again, which is fine. Be careful. Be careful, be careful, be careful, be careful. Make sure u is with u and x is with x. I would recommend this route, and this is what most videos or textbooks would have if you go to look them up. But if it's super complicated or the problem lends itself a little bit better, the boundaries are weird, you can put the x back in. Just make sure you're using x boundaries. Don't substitute a u for an x. Okay, let's look at example 2. That's my teacher soapbox for the morning. What do you suppose u is? I've got 2 sets of parentheses. You want the one with the higher exponent, so it's x minus 3. So du is 1 dx. So when I go to rewrite this, I've got u to the 9th du. That's all happy and good. But then I have this 2x minus 5 sitting here, and I have boundaries. I have the exact situation I told you to avoid. I have u's and x's. It doesn't work. We have to solve this for x. X is equal to u plus 3. So if x is equal to u plus 3, I'm now going to put that in place of this x. So this is 2 minus 5. Here's my u to the 9th du. All right, so I've got everything in terms of u inside. My boundaries, I don't want 2 and 5 anymore. We want to switch those over to u values. So I'm going to use this equation. 2 minus 3 is a -1, and 5 minus 3 is a 2. So this becomes 2u plus 6 minus 5, u to the 9th du, between -1 and 2. Now, I don't want to integrate this right now. There's a product rule, and we'll talk about my product rule for integration later. We're just not there yet. All right, this is what we're looking at like. Before I integrate, what would I do with the u to the 9th? You distribute. So this is -1 to 2, 2u to the 10th plus u to the 9th du. Now from here, it's just a polynomial. Find your antiderivative. So I've got 2u to the 11th over 11 plus u to the 10th over 10 between -1 and 2. So what do I do with the -1 and the 2? You're going to want to substitute them. So this is 2 to the 11th over 11 plus 2 to the 10th over 10 minus 2 -1 to the 11th over 11 plus -1 to the 10th over 10. There's a lot going on here. I'm going to pause this while I do a little bit of calculator work. You do the same. All right, I did a little calculator work while we were paused. So I've put in all the pieces with my exponents. I did the 11th pieces and the 10th pieces together. I don't have a nice neat fraction, but I do get 474.48. And then I also checked my calculator with Math 9. I wonder if I just inverted those numbers. Math 9 has 474.84. So I'm wondering if I made a math mistake, transposing error when I copied that down. But 474, we get the idea. So that's a big problem. Now, example 3, we're going to evaluate 2x over x squared minus 5 dx between 0 and 2. I want to make a note of something that I did not mention the other day. When we integrate, you can't integrate 1 over x squared as it is. You can't do it in the denominator. You have to bring it to the numerator. So this is x to the -2 dx. And I know that we mentioned this in one of the examples somewhere, but 1 over x presents a problem. Because if you bring that to the numerator, it's 1 over x to the -1. And if you try to add 1 to that, you get 0, which is no big deal. But then you have to divide by 0. That is a big deal. Dividing by 0 is indeterminate, and that doesn't work. And that's where we have the natural log. So that's what I'm looking at in example 3 here. This will be a natural log problem. So if I'm dealing with a natural log, which one is the u and which one is the du? These take a little bit of getting used to, but your u is going to have the higher power. And that's because when you take the derivative, you drop a power. So u is x to the squared minus 5, and du is the derivative of that, which is 2x. So if you look, this one matches up perfectly. You have your 2x dx in the numerator. That works. Your x squared minus 5 is in the denominator. So this is du over u. Works out terrific. Now my boundaries are not 0 and 2, but what do we do with those? You put them into your u equation. So the lower boundary is -5, and the upper boundary is going to be a -1. So what is the antiderivative of du over u? Well, it's natural log. Don't forget the absolute value. And that's because your natural log graph only exists on the right-hand side. It's only quadrant 1 and quadrant 4. So it doesn't exist in quadrants 2 and 3. That's why we have to take the absolute value of it. So natural log absolute value of -1 minus the natural log absolute value of -5. So natural log of 1 minus the natural log of 5. But what is the natural log of 1? If you're feeling a little bit rusty from pre-calculus last year, that's a 0. So negative natural log of 5 is the answer. Good. I've got 2 more examples to go over with you. All right, evaluate the tangent of x dx. So this one is indeterminate, not indeterminate, wrong word, indefinite. It's been a long week. This one is indefinite in that I don't have any boundaries listed, which is okay. Let's switch over here to these colors. Tangent of x dx. So you have to ask yourself, is tangent the answer to any derivative problem? When I look at my golden ticket, do I have the derivative of anything is equal to tangent? The answer is no, we don't. The derivative of secant is secant tangent, but I don't have a tangent by itself. So what we have to do is break apart tangent into sine of x over cosine x. And when I look at it like this, we can do u substitution. So which one is the u and which one is the du? Because the derivative of sine is cosine and the derivative of cosine is sine. Well, du always has to be in the numerator. That's the other thing. Du must always be in the numerator. So if du has to be sine of x dx, u has to be the denominator, cosine. So if u is cosine, which is in the denominator, and the derivative of that is actually negative sine of x dx, now we're on our way. So I need to introduce a negative. Let me do that in here. But if I put a negative inside, I need a negative outside. You can call it -1 if you want to. So when we rewrite this in terms of u, this would be du over u. And the antiderivative of du over u is the natural log of u. This one's indefinite, so we get a plus c. And we still have that negative sign in the front. So we can't leave the u there. We have to replace it. Negative natural log of cosine of x plus c. Now, I believe there's a spot on your golden ticket on the integral side for tangent. You will see it like this. But this is not the only version that you'll see. Remember with natural logs and coefficients, those can become an exponent. So this could be natural log of cosine of x to the -1 plus c. Now, this is not inverse cosine. The notation is very confusing, but it's not inverse cosine. It's 1 over cosine. And what else do we know is 1 over cosine? Secant. So I believe that this is the version that we actually see more often, natural log of secant of x plus c. Technically, they're equivalent, but when you go to add this to your golden ticket, use the secant version. If we had a textbook, you don't have a textbook with you. I used to refer to the inside of the front cover, back cover, whatever, had the integrals. Actually, let's do a little search real quick. Integral of tangent x. What's in Safari? The Google. I'll go to the Google. Integral of tangent of x. You can watch a million videos. Oh, see, this one went with negative natural log of cosine. Why can't I not scroll? the alternate form they have secant. So this proof does have both. So they are both acceptable. Just keep that in mind. All right. So we have example 4 done. Example 5, let's talk about E, and this is the last one. So now it's slow when I share my screen. I don't know why it does that. So what's U? I don't have parentheses per se, but it's going to be the exponent. It's 3x. All right, I got to redo this real quick. All right, we should be going quicker now. Here we go. So U is 3x. The derivative of 3x is 3 dx. So when we rewrite this, this is e to the u du. Actually, I missed a 3, didn't I? So I have to put a 3 in the problem and a 1/3 outside. There we go. Boundaries again. Remember, they're no longer 0 and natural log of 2. We have to switch those up. So the lower boundary, 0 times 3 is still 0, so that one stays the same. And 3 times the natural log of 2, we're just going to write as 3 natural log of 2. Don't turn it into a decimal. Anytime you have a decimal, you've approximated it and it's no longer exact. Natural log of 2 is exact. Whatever the decimal you get in your calculator is estimated. So the antiderivative of e to the u is e to the u between 0 and 3 natural log of 2. So we're going to put our boundaries in. 1/3 e to the 3 natural log of 2 minus e to the 0. Now, our exponent friends, you might be a little rusty on these. E to the 0, that one's easy. Always 1. Over here, remember your natural log, we just talked about this. The coefficient 3 can become an exponent. So e natural log of 2 cubed. Now what happens with the e and the natural log right next to each other? Those cancel out. So this is 2 cubed, which is 8, minus 1, which is 7/3. What's up, sir? I will help you get on your Zoom. It is time. So there you go, folks. Last part for these types of integrals. Good luck.